Well, all right, everybody, welcome. It's good to see all of you today. And you guys are the lucky ones. My morning class was a fiasco because they did a fire drill for 30 minutes, start a class, and we lost a whole bunch of time. And I didn't get a chance to do any of the homework for them. So I'm recording my lecture here today so that I can post it up in a little while. And we will hopefully in this class have a little extra time to take some questions on the homework. That's my plan anyway. Most of the homework, though, I don't think is too bad. Mostly finding eigenvalues and eigenvectors of matrices. I think one of them is actually right off of my lecture from last week. So I've already done, whether you know it or not, I did one of your homework problems for you last week in class. And most of the rest of it is mostly straightforward. It's mostly calculational, but I will take some time to do a few questions a little bit later on. Let me spend just a minute to orient you to where we are here because we have 2 weeks until Thanksgiving now. So I just want to make sure we're all on the same page. So today, the homework that you're currently working on is due by tonight. It's number 18. So this is due tonight. And I will try to answer a couple of questions about it during class. I also wanted to let you know that my first office hours at 5:30 this afternoon, they're going to do another fire drill. So we're going to end up outside again, probably until about 6. So if you wanted to catch me after my second class today, that's fine. You can either wait until 6 o'clock when they let everybody back in the building, or you can just come find me. I'll probably be sitting out by the fountain that's out there in the front of the campus with the big arch and everything. I'll just kind of hang out there. You could always ask me a question there. Is that a hand?
Is it just this building that they do?
No, the whole campus.
Oh,
The whole campus is having another fire drill. They already did it once this morning and they're going to do it again. So anyway, just be aware of that. If you're trying to catch me at office hours at 5:30, you might have to go outside to look for me for a little while. Also with this homework, don't forget that there is a video piece to it. It's just a 30-minute little video that I think, well, it's very important. It's about diagonalization, but I'm not actually planning to lecture on that section so much. I actually watched the video again myself the other day, and I think it's pretty comprehensive. It's pretty thorough, and I feel like people can watch that and follow it pretty well. Essentially, section 7.3 is what that video is about, and the hard work of that material is the stuff we've already learned how to do, finding the eigenvalues and eigenvectors of a matrix. The video sort of discusses why we care about that and how we kind of put the information together into this diagonalization process. But the actual meat of the calculations is very, very easy at that point. So that's why it's a pretty short video. But it's absolutely required viewing. Make sure that as part of your homework for tonight, you watch that video and submit those notes for me. So that is for tonight. The next homework is the one that there may be some more questions coming, and I will take questions on it for Thursday. This one is actually not due until Friday, but this will cover that diagonalization technique that's in the video that you're watching. And also the first part of chapter 8, which is what we're going to be jumping into here today. So definitely feel free to get started on that whenever you're able. The next homework after that will be due on next Tuesday. And this one, homework number 20, is a very short assignment. It is probably doable in 20 minutes. It's the section 8.2 is widely viewed by most students as like the easiest section of the entire semester. It's really quick. So you'll have no trouble with this homework assignment. But next Tuesday in class, we're going to be doing some group works. And in addition to that, you guys may remember that for each exam, I've been offering an extra credit video and an extra credit quiz to add points to your exam. So there will be a video for you to do over the Thanksgiving break. I will have a video for you to watch as extra credit. But in addition to that, I'm going to have an extra credit quiz, but this time I'm going to have it in class. So this will be extra credit, so it's not high pressure, but we are going to have next Tuesday in class, in addition to doing some group work, we're going to have an extra credit quiz number 3. So it will be worth roughly 3 or 4 points towards your next midterm. Okay, so instead of doing it as a take home, I want to do it in class next Tuesday. Part of the reason for that is that when we come back from Thanksgiving break, we will be pretty busy getting ready for the midterm that follows the break. So I don't want to have you guys burdened down with a whole nother thing to do. So I'd like to do this before the break. So next Tuesday, we'll be doing that. It will be closed notes, closed book, and it will cover, sorry, I should point this out. This will cover chapters 6 and 7, which we are basically already done with. More or less, we're done with that. And again, it will only count like 3 points of extra credit. So it's not super high pressure, but I do want to do it in class rather than as a take home this time around. Okay, that way you won't have to worry about it later on. Are there any questions about any of that? It's kind of the schedule here as we head towards the Thanksgiving break. Okay, if everybody is good with that, what I'd like to do today, guys, is the thing I've been waiting for quite a few weeks now, which is today is the day we are going to finally go back to differential equations again. And these last 3 to 4 weeks of the semester, we are going to be using the linear algebra that we have been learning for the last 2 months. We're going to now use that linear algebra to help us better approach the process of solving differential equations. And in particular, chapter 8 is going to be about differential equations of order n and the ones that are linear. Now, the good news here is that most differential equations in the real world are linear, and they are usually, of course, of some order n. So this type of differential equation is exactly the ones that you see in engineering, physics, biology, and a host of other applications. And so this is definitely something we want to be talking about. So we're going to discuss this. And I don't know if you guys are going to take any bets on how long it's going to take before we start talking about linear algebra right away. It's not going to take long, like less than 5 minutes. Okay, because the whole idea here is to use the linear algebra now to help us with this. Right, so let's set the stage for this new chapter. It's a totally new topic today, right? These are just some notations that I'm going to be using in this talk. So I, capital I, is going to just represent some interval on your x-axis, right? Some domain. It could be a closed interval, say from A to B. It could be the entire real number line, which we could denote with minus infinity to infinity. Usually what I is going to really be is just the domain of whatever functions are in the universe that you're working in. So for example, the natural logarithm. We all know that the natural logarithm is only defined for positive input values. So in that case, your interval might be just from 0 to infinity. Okay, so the domain, this interval is not going to play a big role in what we're doing. But just so you're aware of why it's there, it's to sort of create a domain where the functions that you're working with will be defined. Okay, so no big deal on that. And then I created these sets here. All of these, as it turns out, these are all vector spaces. C super 0 of I, these are just the continuous functions that are defined on I. They take inputs from I. So these are, just think of it as calculus functions, and you'll be fine. Okay, we are also, of course, we're talking about differential equations. So that means I'm going to be taking derivatives of the functions that I'm looking at. And in order to do that, I've created sets for that as well. So C super 1 of I, well, that's going to be the differentiable functions defined on I. These are functions that you can at least take the derivative of them, right? Okay, and then maybe we can take multiple derivatives. 2 derivatives, 3 derivatives, 4 derivatives, whatever it might be. So if we want to take functions where it is possible to do k successive derivatives of those functions, I'm going to denote that here, right, with the C super k of I. Right, this is just those calculus functions that you can take up to k derivatives of them and still defined on the same interval I. This is just notation. And for the most part, that will all be in the background of what we're going to be talking about. I mean, really what our goal is, I just want to get the big picture of this again. The goal is going to be to learn how to solve these differential equations. That's what we want to do. That's what the engineers are going to care about, the physicists, the biologists, and anybody with an applied interest in what this math is good for. We want to solve these differential equations. So that's really what we want to get to. It's just going to take a minute to set up some of the background for this. So I'm going to put a little definition here to kind of get the conversation started. And I'm going to define this derivative operator. So define the derivative operator. And this is going to be denoted with D. So D is the operator notation for this. And D is going to go from C super 1 of I over to C super 0 of I. Okay, and so I'm going to input a function from the C super 1 of I. That means it's a function that's differentiable. And I'm going to apply D to it. So I'm going to take D of F. And the formula for this is going to just be F prime. We are literally just going to take that derivative. We're just going to take this derivative here. More generally, we define, I'm going to more generally define D to a power. So maybe I take the kth power of D. This one is going to take a function on I that is k times differentiable and spit out something that is a calculus function here. And this time, it is going to be defined as follows. D super k, sorry, the kth power of D applied to F, well, this is going to be k derivatives of F. So we'll take k derivatives of F. Okay? So you're going to see me using this, what I call the D notation today quite a bit. But the big remark here, okay, we just took bets on how long it would take before I started talking about linear algebra again. Well, here it comes. Here it comes. The remark is that this operator D is linear. It's a linear transformation. Okay, linear transformation. So that's chapter 6, right? Does anybody want to remind me again? What does it mean for a function to be a linear transformation? Evan? You're thinking of a basis. Marcus?
Respects.
Exactly. To be linear, the operation has to respect addition and scalar multiplication. And that is certainly going to be true. That is certainly going to be true, guys. D respects addition. Right, let's just write it down. Like, how does this look? If we take D of, say, F plus G. So if I take two functions, I add them together and I apply D to that. Well, this just means that I'm going to take the derivative of F plus G. Anytime I see a D of whatever, I just take the derivative of it, right? So this, as we learn in calculus, the derivative of a sum of two functions is the same thing as the sum of the individual derivatives, you see? So I can write this as F prime plus G prime, and that is just D of F plus D of G. So D respects addition, for sure. Right, so D will respect addition, and similarly, D also respects scalar multiplication. And that's going to look very similar. When I use scalar multiplication, I usually use a scalar k in front of my vector, right? And so D of kf, this would just look like, okay, that's kf prime. And if I take the derivative and there's a constant in front of my function, what am I allowed to do? Take the constant out. Exactly. That's something we certainly know from calculus. So this just becomes k times f prime. And that's nothing more than k times d of f. Okay, so taking the derivative is an operation that is linear. It respects addition and it respects scalar multiplication. And my friends, if this was not true, if this remark was not true, we would not be here right now. there would be no Math 250B. It wouldn't make sense to talk about linear algebra in the same semester as we talk about differential equations, right? Because we wouldn't be able to use the linear algebra to our benefit so much if anytime we had a differential equation, there was nothing linear about it, right? If we couldn't leverage any of the linear algebra that we've learned, then we wouldn't put these two topics together in one class, right? So this fact right here, as easy as it is to write it down and to kind of explain it, it's a big deal. It's a really big deal. If anybody ever asks you, oh, why did they teach, why did you learn differential equations and linear algebra together, right? One of the big selling points should be that taking derivatives respects the vector space operations of addition and scalar multiplication, okay? There are plenty of universities that do not put these two classes together, right? So you'll find plenty of people out there who might wonder, oh, I wonder why you took those two subjects together side by side. Well, now we have at least a little bit of a reason why we do that. And we're going to have a lot more reasons as we kind of go through today's talk. Okay, is everybody with me so far? So far, so good? You know what? I really should remind you what this linear differential equation of order n looks like. I say remind you because we have actually done it before, and it was way back in August. At the very first couple of days of the semester, I had you probably watch a video about what is a linear differential equation anyway. So I want to put it back on the board because we are going to need this to be able to talk about well, chapter 8 is all about solving these equations. So just recall here, guys, from way back at the beginning of the semester, that the form of an nth order linear differential equation is the following. I'm going to write down the form for you here. Again, this is probably already buried in your notes somewhere from way back when, but we're going to just recall it. So we have a0 of x times n derivatives of y plus a1 of x times n minus 1 derivatives of y and plus dot, 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 plus a sub n minus 1 of x times y prime. And finally, a sub n of x times y. And this is supposed to be equal to f of x. Go ahead and put a box around this one. It's kind of long, a little bit cumbersome to write that down, but that is something that will probably be already in your notes from literally the first day or two of the semester. This is what an nth order linear differential equation looks like. The a0 of x, the a1 of x, and so on, those are just functions of x that could be anything, really. Now, they might be limited to some interval I, and so that interval I would then play a role in how this was defined. But the key thing here is you'll notice that every single one of these terms has exactly one of the derivatives of y in it, and there's no mixing of the derivatives together, and we're also not doing any fancy footwork with the y itself. You notice there's no square root of y. There's no e to the y. There's no cosine of y. And there's no y times y prime. We're not mixing the different derivatives together, right? Every single one of these expressions of y has its own term all by itself, not mingling with any of the other derivatives of y. That's what makes this linear, okay? So yeah, we have written this down before, but what I would like to do right now, guys, is rewrite it down again using my D notation. This D notation that we just introduced will be kind of a nice way to rewrite this. So I'm going to rewrite this in D notation. I'm going to try to rewrite this in the D notation. So how's that going to look? I'm also going to start suppressing the x's here. I won't be writing those down every time. So if I start this off, I have a0, and then I have n derivatives of y. Well, that would be n powers of d, right? And then I'm going to just put of y over here. And by the way, the capital F stays the same. on the right-hand side. So I'm just gonna think of this as the first term is a0 times n derivatives of y. And then we're gonna add to that the next term. The second term would have a1 times n minus 1 derivatives of y. And we keep adding these terms together. As we work our way to the right, we have a sub n minus 1 times d, just one derivative of y here. And then finally, we have an a sub n, which just directly multiplies with y, right? So I can actually write it in this nice d notation. So this is the same exact thing, it's just written using our d's now instead of the primes that we have above. So probably ought to emphasize this one as well. Okay, so that's the d notation. And I should also point out, I mentioned that the d operator is linear, but actually, in fact, point of fact, all of the powers of d are linear. If I had done this with the second derivative, or with the third derivative, or the fourth derivative, all of these calculations would have carried exactly the same way through. And we would say, yeah, all powers of d respect addition and scalar multiplication. And that actually means that all of this whole entire thing, which I'm going to call L, is fully linear. It's, after all, it is a combination of things that are already linear. So let's call this L, and the remark here is that L is linear. It is a combination of smaller operators, each of which individually is linear. And so the full L itself is linear, okay? And so what you've noticed here now is that if I call that whole thing L, then my differential equation is simply L of y equals F. If we want to put it into the most condensed notation of all, that's how it would look. Okay, so this is how I'm going to be writing my differential equation in chapter 8. I'm going to write it with some derivative operator L applied to my unknown function y. F of x is given to me on the right-hand side. And of course, the goal here, it's always good to keep a roadmap of what are we trying to do with this whole thing. The goal is, of course, to solve this for y. All right, the unknown function in this differential equation is y. So solve for y. Okay, so that is ultimately what our goal is going to be. Solve for y. Does this make sense? Everybody with me? You know, the nice thing about chapter 8 is there's not a whole lot of vectors flying around. There's not a whole lot of matrices. It's kind of a break from some of that more technical notation. Everything can be written down a little bit more easily. So somebody came in here over the weekend and used hand sanitizer wipes on this board. I'm finally, by 2 o'clock in the afternoon, getting to a point where I can erase this board a little bit better. This morning, it was just a nightmare. I don't know, this room is usually locked up, but somehow it was reminding me of my COVID teaching. When COVID was going on, I actually moved to Colorado for a while because I have a summer place. I live out there in Colorado, up in the mountains at about 9,000 feet. And I was just teaching out of my garage for a whole year during COVID. And when the weather got colder, I noticed that, because I didn't want to have marker all in the house and everything. So I just did it out in the garage. But I noticed when the weather got colder that I was having trouble erasing my whiteboard. And I realized that I didn't know this, that if it gets below about 50 degrees, it becomes extremely difficult to erase a whiteboard. And this morning I was remembering this. I was like, am I back in COVID times again? I can't erase this board. Somebody used these disinfecting wipes on the board, which was really bad. Oh yeah, I remember I had to like go buy a space heater, and I would blast the heat onto the board like during my class. I was literally trying to teach through Zoom at that time. And that was the only way I could erase it. But the problem was the space heater was noisy. So I had this like echoing motor through my garage, and then people are in Zoom trying to talk. It was a rough time, right? You guys remember, you were living through it too from the other side. Anyway, so yeah, I was being reminded of that this morning. Yeah, so anyway, just to make sure we understand how this operator L works, I thought I'd just throw one quick example up here for you. Just to practice it for a minute, and then we're going to spend most of the rest of today tackling that goal over there. The goal is to solve for y, so let's not lose sight of that. But before we do that, I just want to make sure people understand how this L works. So let's just take an example. Let's let L equal x minus x squared times d squared. Okay, and then plus the sine of x times d, and then plus 2x plus e to the x. So let's make that my L, and then I'm going to let y be equal to e to the 3x plus 2x. Okay, so let's just take this as an example, and here's what I'd like to do on this problem. I would like to just compute what is L of y. Okay, this L of y showing up here, right, on the left side, kind of important. It's an important piece of the differential equation. So I just want to make sure everybody understands kind of how this all works, okay? Because it's kind of abstract when you first just look at the notation. When I'm thinking about solving this one, maybe before I really get into it, can somebody tell me for this example, what would the n value be? Just 2, right? The n is just the highest number of derivatives that you see, right? The largest power of d. And right here, I see that d squared is the largest power of d that we have. So n is 2. And so what you could think, if you wanted to, guys, this coefficient x minus x squared, that's really a naught. Sine of x, that's just a 1. And 2x plus e to the x, that's just a 2. So we would have those coefficients here. Okay, so with that in mind, what I'm going to do is I'm going to kind of try to write down what L of y is now. So I'll go ahead and put in my my operator L, which is x minus x squared times the quantity d squared plus sine of x times d, and then plus 2x plus e to the x. All of that bracketed part is just recopying what L was. I now want to input y into that. So I'm now going to stick the y right over here on the end of it, e to the 3x plus 2x. And what I need to do now is calculate this thing right here. So let's just make sure we understand how this works. I'm going to start from left to right. I have x minus x squared. We just recopy that one. And then what does this next thing say? It says d squared. Now that's d squared of y, right? So 2 derivatives of y. Let's go back and rewrite that using the prime notation. So 2 derivatives of e to the 3x plus 2x. Okay, that's the way that one would look. Okay, and then we're going to go plus, right? And now my next term has a sine of x on it. So I start off with sine of x, and then I have d. That would be d of e to the 3x plus 2x. So I'll write e to the 3x plus 2x. This time I'm taking 1 derivative of it. Okay, and then the last term, we'll add one more term here. The last term is literally just this times this. And I'm not even going to multiply it out. I'm just going to sort of smash these 2 factors together. So I have 2x plus e to the x being directly multiplied by e to the 3x plus 2x. So that's the way that last term would look. And to get to my final answer, I just need to calculate a couple of derivatives. Does anybody remember how to do derivatives around here? After so many weeks of linear algebra, we weren't really doing a lot of derivatives. But now, of course, we're going to be doing them again since we're moving back to differential equations. So I have to take some derivatives here. Can somebody help me? What would be 2 derivatives of e to the 3x? Chris?
9e to the 3x.
9e to the 3x. That looks good. And to that, we have to add, what's 2 derivatives of 2x? That's just 0. Okay, so that's the first term there. Okay, and then on the next term, we'll add to that sine of x times 1 derivative of e to the 3x plus 2x. Empty
3e to the power 3x.
Okay?
And then plus 2.
And then plus 2, exactly. So that's the first derivative. And then the last term, we can just recopy it as is. We don't have to actually do anything with this. 2x plus e to the x times e to the 3x plus 2x. Okay, so I just wanted to make sure people understand how this L operator works. Essentially, it is just some, mishmash of derivatives, right? That have to be applied term by term by term as you go along here. Okay, is everybody all right with that example? We'll feel okay with that? Okay. If so, then let me come back over here. And give myself, take a minute to try to erase this. On the bright side, I won't have to go to the gym this week because my arms are getting a pretty good workout. Just trying to get this stuff off of here. Not that I'm much of a bodybuilder or anything, but yeah, so anyhow, this is where we're at. Okay, questions so far? Yeah, Audrey,
Just the first line, L of Y.
this one?
Yeah, and then the right side of it, so we're plugging in for D, right? But then
This is
Why are
just
we
L
multiplying?
here, and then this was just Y here.
but it's not like multiplying.
It's
L.
not multiplying, because it doesn't really make sense to multiply, it's really the function inputted with this. So you're inputting Y into L. I mean, it's just the way, if you write a function down, you're gonna input something into it. And so you would view this as being that input. That's essentially what's going on there. Okay, yeah. Okay, all right, so let's see. Our goal here, guys, our goal is to solve this differential equation for Y. Turns out that's a little hard to do in general. So by Thursday, we will fully address that. But for today, we're going to lower our sights a little bit, and we're only going to look at a special case of that, namely when the capital F is 0. If that right-hand side is 0, then all of a sudden it's a much easier problem to study. So I'm going to make a definition here for that, which is that given the differential equation L of Y equals F, the associated homogeneous, so here's a word we've seen before in other places, we're using it again here, the associated homogeneous differential equation is L of Y equals 0. So if we just take the capital F and we sort of throw it away and we just make the right-hand side 0, we're going to call this a homogeneous differential equation. And it turns out that the first step to this general project of solving for Y right here, the first step, my friends, is going to be to solve the associated homogeneous differential equation first. We're going to do that first. So this is going to be, for the rest of today, this is the only thing I'm going to worry about. I'm not going to worry about the capital F on the right-hand side, but stay tuned because on Thursday, I'll be talking about that. Okay, so in this case, we are trying to solve this for Y. So we still want to solve for Y. Now I have to ask you, when you're thinking about solving this for Y, does this look familiar to you from anywhere in this semester? We have a linear operator, a linear transformation. We're plugging in Y and setting it equal to 0. And we're trying to solve for Y. Does that sound like something we've done recently? What was it? David, you're nodding your head.
Math.
Even just a little bit before that. You have an idea?
Finding the.
A little bit after that. Evan? The kernel. The kernel. It's the kernel. Guys, do you remember this thing? we had T of V and we would set it equal to 0 and try to solve for V. That's how we solved for the kernel in chapter 6. Just a couple weeks ago, we were doing this, yeah? So we would be solving for this unknown V by setting T of V equal to 0. Well, honestly, this is literally the same thing, except instead of T, now it's called L, and instead of V, now it's called Y. But it's the same thing here, guys. We're actually trying to solve. So let's just add to this little comment here. We still want to solve for Y, which corresponds to the kernel of L, right? If we solve that for Y, we're actually looking for the kernel of this linear operator L. Yeah? Oh, well, if this is the kernel of something, if what we're trying to find is the kernel of something, oh my goodness, are we in business? Are we in business? We have something that is a subspace, right? We learned in chapter 6 that the kernel of T is always a subspace. Oh, that means it's going to have a basis. It's going to have a dimension, right? And we could be trying to focus on figuring those things out, you see. This is exact. In fact, if we find a basis for the kernel of L, then that actually means that's a spanning set so that every possible Y that solves my differential equation would be expressible as a linear combination of that basis. Oh my gosh, this is exactly why linear algebra is so incredibly important here to this theory. And in fact, I'm going to state a theorem now that will guide us in the next steps that we're going to take. Okay, so this is a nice theorem about this, which is that the set of solutions to L of Y equals 0 for Y, so we're solving L of Y equals 0 for Y, forms a vector space. I mean, I said a moment ago it forms a subspace, but remember that a subspace is just a vector space. So it forms a vector space, and even better than that, even more than that, we can actually say what its dimension is. The dimension of this vector space turns out to be the same n that we have in the operator L itself. So L has, a power of n here as the largest power. And whatever that n is, that's the dimension of this vector space. So I'm just going to remind you here where L is, I'm just recopying from that board over there, A naught times d to the n plus A1 times d to the n minus 1 and dot, dot, dot down to A1n. So that's basically what we're talking about here. Guys, we actually know the dimension of this thing. So we know how many basis vectors it would take to span the solutions to my differential equation. That's hugely powerful. Let's do an example. And I just want to make sure everybody's totally on board with this. Let's suppose I ask you to find the general solution. Find the general solution to so let's make a differential equation here. I'm going to use d squared plus 1 of y equals 0. Let's just take this one as a first example to play with. Okay. So this right here, this is my L, right? L is just d squared plus 1. For those of you who are still kind of adapting to the d notation, we can write this without the d notation. 2 derivatives of y would be y double prime. And then 1 times y would just be y. So this is just another way of expressing the differential equation that I've just put in the brackets there. Y double prime plus y adds up to 0. And so what I'm curious about right now is let's forget about Math 250B for a minute and just try to remember back to calculus. Can anybody think of any solutions to this differential equation kind of just off the top of your head? Not based on anything we've learned here, but just based on calculus. Can anybody think of a function that after you take 2 derivatives of it, it cancels out what you started with? Has anybody done any calculus lately? Evan? One more time,
Sign it.
sine of x. Okay, has anybody taken two derivatives of sine of x lately? If you take the derivative of sine x, you get cosine. You take the derivative of that, you get negative sine. Although negative sign added back to sine would cancel out to zero, right? So I'd just like to note that sine of x, well, let's give this a name. I'm gonna call it y1 of x equals sine of x is a solution. Okay, can anybody think of another solution that you know from just kind of glancing at it, just from calculus? Has anybody got another idea? Let me hear from somebody I haven't heard from yet today. Have I heard from you? I think I have. Anybody want to take a stab at it? Hasn't had a chance yet? Can you think of another function besides sine of x? Okay, I'm gonna let you go for it. Audrey, I'm gonna let you go for it. A constant function. So if I put 7 in for y, then two derivatives of 7 would be 0, and I add 7 to that, I don't get 0.
Oh,
So I would say constant probably isn't gonna be the place to look here, actually, turns out. Yordi, how about cosine of x, right? Cosine of x. If you take two derivatives of cosine of x, you're gonna get the negative of cosine of x. That's exactly right. So let's just add that here also. Y2 of x equals cosine of x is a solution. So we have actually just come up with a solution, right? And by the way, on this problem, what is n equal to? Right, the n value is 2. So what does my theorem say? My theorem says that the solutions to this differential equation forms a two-dimensional vector space. And look what I have here, my friends. I have two solutions to my differential equation. That's sounding like it could be a basis of solutions. It could be a basis word. Okay, let me. I'm so excited, but I can't write anything down, so I get this off of here. Okay. Yeah. So I actually claim that these two functions are actually a basis for the solution set. And that is really the main objective of this, is to find a basis. Because if you have a basis, right, then you can take all of its linear combinations and find you know, the whole span of these two solutions, right? So let me just make this as a little note here, right? The set of sine of x and cosine of x. Well, actually, before I go, I don't want to jump too quickly here. In order to call these vectors a basis, what are the conditions for a basis again? Liam? Okay, they have to be a spanning set and they have to be Li, right? I would like to first try to convince you that they are Li. Let's just discuss the Li piece of this first. How do we know that these are Li? Chris?
They have to equal to 0.
Well, Li had, let's be careful. Li would mean that, you know, if you had a linear combination of these that canceled out to 0, then the scalars would all be 0. But there's a easier, just glancing at it, reason that we could give here, I think, that might be a little bit nicer. Dorsa? Two vectors. Two vectors will always be Li if there's a condition.
They are not scalable.
They are not scalar multiples of each other. Exactly right. Does anybody think these are scalar multiples of each other? No way. In fact, they are shifts of each other. If you draw the graphs of these two functions, they're just horizontal shifts of each other. They're not scalar multiples of each other. So this is Li since sine of x and cosine of x are not scalar multiples of each other. Okay, they're not scalar multiples of each other, so they are Li. But now, remember that if we believe this theorem, the dimension of the solutions is 2. Right? In other words, the dimension of my vector space is 2. How many vectors do I have here? 2. So it's the right number of vectors. That means that this set is both or neither, right? Remember that whole thing where you had the k value and then you had the dimension. If the dimension is 2, right? And if k is 2, then because they're Li already, then they must be a spanning set. In other words, they are definitely a basis. Okay, so let's just say since k equals the dimension equals 2, right? We conclude, comma here, right? We conclude that this set, sine of x and cosine of x, is a basis. Is a basis of solutions to the differential equation that we were given. That is a basis of solutions to the differential equation that we were given. Right, so that's the powerful observation. And if they're a basis, that means they're also a spanning set. It means that every solution to our differential equation, every solution is a linear combination of those two, right? So thus, the general solution, right? When I'm asking for the general solution, which is what this question is saying, the general solution is, right? How do we get the general solution? Well, we take linear combinations of our basis vectors, right? So let's write it here. Y of x equals C1 times the sine of x plus C2 times the cosine of x. That's going to be it. That's going to be it. I'm not convinced that everybody is quite appreciating the power of this yet. Let me say one more comment here. The exciting thing about this is not that sine of x is a solution or that cosine of x is a solution. You guys could all have figured that out, right? What's exciting is that after you find these two solutions, you might not have known. If we had done this 10 weeks ago, before we had the theory of dimension and basis and vector spaces in our hands, we might not have known that these were the only solutions we really needed to find. We might have wondered, oh, could I go home tonight and maybe there's some crazy combination of logarithms and radicals and fractions that somehow magically two derivatives of it will cancel it out and I'll have another solution, right? We might be wondering, could there be some weird solution to this differential equation that's not just sine and cosine, right? The power of what I've put over here, and really the power of this theorem, is that all solutions to this differential equation are captured here. There's nothing missing, right? So as soon as I find sine and cosine, and then I take linear combinations of those two, I'm actually getting every solution that there could ever be to the differential equation. We could not have said that without linear algebra, without knowing that a basis means you have a certain number of vectors, which is the dimension, and you don't need to look for any more than that. So powerful. Okay, so I don't know. You guys don't look all that excited about it, but it's pretty darn exciting. It's a pretty big deal. The fact that we don't have to keep looking. Isn't it nice to know that, oh, well, once we find two linearly independent solutions to our differential equation, we can pretty much rest comfortably in knowing that all of the solutions are just built out of those two. That's a pretty big deal. That's a pretty nice observation. Okay, so anyway, I guess I'll appreciate it on behalf of everybody, which is good. No, I think you'll really begin to appreciate it more as time goes on. So there is one little issue though here that I want to talk about. You know, you might Well, there's a couple of issues. One issue here is we kind of got lucky to just happen to notice that sine of x and cosine of x were gonna work here. What if my differential equation was maybe not so transparent and we couldn't come up with these solutions to begin with? So that's one problem. We've got to come up with the basis solutions in the first place. Otherwise, all this theory doesn't do us a whole lot of good. The second issue is that we also got lucky on this example because it was really easy to convince ourselves that sine of x and cosine of x were Li. But what if n was 5 and I had 5 different functions in front of you and I asked you whether those were going to be Li or not, right? Normally the way we would test for Li, if you might remember from a few weeks ago, we put our vectors, if you recall this, we put the vectors into the columns of a matrix. We would augment that matrix with a column of zeros. We would do a bunch of EROs. And then, well, if there were no free variables, we could say, yeah, the vectors are Li. Remember that? So well, that's how we handled it if, we had slots or if we had polynomials or matrices, right? But you might have noticed that we didn't talk a lot about how to test for Li when your vectors are actually just functions. I mean, how would you put sine of x into a column of a matrix or cosine of x into a column of a matrix? It's not so clear. So I want to address that question really quickly here. And then once we get this kind of out of the way, we'll take a little break, okay? So I'll put this question here. The question is really just given n solutions. Let me call them y1 of x, y2 of x, and dot, 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 up to yn of x of a differential equation. If we have n solutions to it, the question is, how can we tell? How can we tell if that set, let's say y1 and y2 and dot, 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 up to yn, how can we tell if that set of vectors is going to be Li? Okay, again, this example was too easy. Sine and cosine, yeah, I know those are Li because they're not multiples of each other. Easy enough. But what about over here? What about in general? Well, there's an answer to this that I can give you guys, which goes by the name of a mathematician who is credited for this. He's a little bit of a crazy guy. I didn't get a lot of credit for a lot of things. His name is Wronskian. So this is called the Wronskian of these functions. And let me explain what that is with a definition. What am I talking about here? When I talk about the Wronskian, there's a definition for this. And what it is, I'm going to write it as W of y1 and y2, comma, dot, 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 up to yn. And this is going to be of x. And what this is, okay, I promised you there's not a lot of vectors or matrices in chapter 8, but there is one. There is one, and it's the one I'm about to write down. Give yourself plenty of room, guys, to draw out this matrix notation here. So I'm going to take the determinant of a pretty large matrix. And the way that you set this up is you actually lay your functions right across the top row of your matrix right here. So y1, y2, and so on, you lay those as the first row. And then what you're going to do to fill out the rest of this matrix is you're going to start taking derivatives down the matrix. So the second row is going to be y1 prime, y2 prime, y3 prime, and dot, 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 up to yn prime. And if I go to the next row, I'm just going to take yet another derivative. So the third row would be y1 double prime, y2 double prime, y3 double prime, and so on. Okay, and you might wonder, well, how long do you keep doing that? How long do you keep taking derivatives down the matrix? Well, it's very easy because if you want to take the determinant of something, it has to be a square size matrix. So you keep taking more and more derivatives until it is a square n by n shape. And so the last row would actually be n minus 1 derivatives of y1, and then n minus one derivatives of y2, and so on, right? N minus one derivatives of each of my functions like so, okay? So this is what I'm talking about when I talk about the Wronskian. And what is the actual theorem then that sort of allows us to decide if my functions are Li or not? Well, it's actually very simple. The theorem just says that if there is a value of x. Oh, just to be really clear, does everybody understand? This is not a matrix of numbers. This is a matrix of functions that we are taking derivatives of. So you're going to see x's scattered all over this matrix, right? Its entries are just derivatives of functions. So this is really a function of x. If you were to write out what it is, it's a function of x. And if there is a value of x, let's give it a specific name, say x naught, such that w of y1 comma y2 comma dot 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 up to yn of x naught is not 0. If we can find even one number to plug in for x that will make my determinant not 0, that's always a good thing, right? If the determinant is not 0, this would mean the matrix is invertible. And so then that's a good thing. That means that my functions y1 and y2 all the way up to yn, that whole set of functions, yes, they are Li. That is a linearly independent set in that case. Okay, so that's pretty cool. All right. Let's take a minute and do an example or two of this Wronskian idea, and then we'll take a 10-minute break, okay? So this is the theorem here. Hopefully it's making some sense. But let's just do, just as an example, so everybody kind of gets the feeling for this. Let's just go back to the one we already looked at, which is sine of x and cosine of x. And I just want to make 100% sure that everybody's convinced that those two functions form a linearly independent set, okay? So here I'm going to give the reason. Why are those functions Li? Well, if I take the Wronskian of sine of x comma cosine of x, so we already have one reason over there, right? The two functions are not scalar multiples of each other, but just to practice our new tool, this is a new tool for testing linear independence. I just want to try it again. So this is going to be what? A determinant of, again, give yourself plenty of room to write it out. I just put the two functions on the top row. So I'll put sine of x up in the upper left corner, cosine of x in the upper right corner. And then how does this work again? Well, I start taking derivatives. So the first derivative of cosine of x is, first derivative of sine of x is cosine. First derivative of cosine is negative sine. And how long do I keep taking those derivatives for? I do it until it's a square matrix. I can't take a determinant unless it's a square matrix. So at this point, I already have a square matrix. For a 2 by 2, I think we all know the little 2 by 2 determinant formula, right? So AD minus BC, that's going to be negative sine squared of x and then minus cosine squared of x. And does anybody know what that equals?
1.
It equals 1, but then there's a minus sign, right? So it's to just be negative of 1. That's like the famous trig identity. Cosine squared plus sine squared of x always adds up to 1. So this is just a minus 1, but what's really important is that it's not 0. And in fact, guys, it's actually never 0. In this case, here, this just says you have to find one value of x that makes the determinant not 0. Turns out that in this case, you can plug any number in for x that you want, and you will never get 0 out of it. You'll never get 0. So that's a pretty good justification. Using this theorem now, these functions are Li. Okay. Everybody with me on that? Any questions on this Wronskian? So we're addressing the issue that we need to make sure that we have linearly independent functions to serve as our basis for our general solution, right? As soon as we know that sine of x and cosine of x are Li, then we can take all possible linear combinations of those, and that will span the solutions to my differential equation. These guys are a spanning set, and they are Li, right? They are in fact a basis. Okay. Pretty amazing. There's a lot of linear algebra in this, even though we've kind of moved back into the realm of differential equations. Let me do one more example of this Wronskian thing, and then we'll take a little 10-minute break. My morning class was all screwed up because we had to go outside for 30 minutes at the start of class, so we didn't take any breaks at all. I just went cruise through this whole thing, but I think we'll be able to take a break for this class. So let's take the set 1 over x, 1 over x squared, and 1 over x cubed. And I'm going to try to convince you again that that is Li. Let's check this out. Let's check this out. Okay, so again, I'll put reason here. And we're going to try to check this one. Okay, so I'm going to do my Wronskian again. So this is W, right? Of 1 over x, comma, 1 over x squared, comma, 1 over x cubed. We're going to take the Wronskian of all three of those functions. So again, I'm going to use this tool, which is the determinant. Again, make plenty of space for this because this is not a matrix of numbers. This is a matrix of functions. And again, the first row is very easy. You just write down your functions into the first row. 1 over x, 1 over x squared, and 1 over x cubed. That's your first row of your matrix. And how many derivatives do you think I'm going to need to take this time? Tina?
2 derivatives.
I'm going to need up to 2 derivatives to make this into a 3 by 3 matrix. Okay. So let's just start getting into it. Let's take the derivative of each of these. The derivative of 1 over x is, you can use the power rule if you wanted to. Be careful not to do integrals here. This is derivatives, not integrals. Like somebody this morning said, oh, shouldn't that be the ln of x or something? No, we're taking derivatives here, not integrals. So we would get negative 1 over x squared. This one would be negative 2 over x cubed. And this one would be negative 3 over x to the 4th, like so. Just using the power rule for derivatives. And then I have to do that one more time to get the bottom row of the matrix. So this should be 2 divided by x cubed, and then 6 divided by x to the 4th, and then 12 divided by x to the 5th. So this is a matrix of functions. It's not nearly as easy as just dealing with numbers. How would you suggest I go about finding that determinant? It's a 3 by 3. Liam?
You could do the one where there's 2 rows.
Columns?
Yeah.
And do what?
The arrow method.
Yeah, it's the arrow method, exactly. So the arrow method for a 3 by 3, I just recopy the first 2 columns here. It's exactly what I would recommend. So I'm just going to copy the first 2 columns off to the right, like we used to do in chapter 3. And then I'm just going to do my arrow method, right? I'll just do my arrow method here. So I'm going to do this relatively quickly. The first diagonal here, right? You can see, what is that? In the numerator, I have a 1 times a negative 2 times a 12. That would be negative 24. And on the bottom, I have x, x cubed, and x to the 5th. You add up all those powers of x, it's x to the 9th, right? So that's the first diagonal. And then I just shift over to the right, and I do the same thing again. This time I have a 1, a negative 3, and a 2. That's negative 6. On the bottom, I have x squared, x to the 4th, and x cubed. If you gather up all of those powers of x, you also get x to the 9th. And in fact, all of the denominators are just x to the 9th every single time. Every single time. So this one is x cubed times x squared times x to the 4th on the bottom, which is x to the 9th. And on the top, we have minus 6 as well. So negative 6x to the 9th, like so. All right, and then remember, we have to also do the arrows going this way, and those are with sign changes. So if I look at the diagonal here going this way, 2 times negative 2 times 1, that's negative 4. But because it's a sign change on that diagonal, we have to write it as a plus 4. And it'll still be over x to the 9th. The next one, 6 times 3 times 1 is 18, but it's going to be with a plus. And we're still going to be dividing by x to the 9th again. And the last diagonal is going to have a plus 12 divided by x to the 9th as well. Okay, so this is the arrow method. If you make a common denominator of x to the 9th out of everything, and you just clean this up a little bit, so let's see, if I take negative 24 minus 6, that's negative 36. But to that, I'm going to add 34. So negative 36 plus 34 is actually negative 2. So we'd have a negative 2 on top, and I hope I've done that right. But the point is that it is possible to plug in a number for x that would make this not 0. In fact, you could plug in almost any number. There's only one number that would be off limits here, which would be what? 0. I would not use 0. But then again, I wouldn't really ever use 0 anyway, because you can't even plug 0 into the original functions. So this is still not 0. And again, we would check that off, that the Wronskian is not 0. And that means that my functions are Li. My functions are Li. Right. Okay. Pretty nice. Okay. I think I've laid the groundwork for going back and approaching our goal. So remember I said there are 2 issues with this example over here. One issue was, well, how do you tell if functions are Li in general? I hopefully have explained what we're going to do for that. The Wronskian is our big new tool today. But then the second question was, well, how do I come up with the basis solutions in the first place? Here we kind of got lucky. We had a couple people in the class who happened to notice that, 2 derivatives of sine of x canceled out sine of x, and 2 derivatives of cosine canceled out cosine. But what if you don't see it off the top of your head? Like, how are you going to actually come up with these basis solutions if it's some weird equation? So that question I have not addressed yet. So I would like to hold you in suspense for 10 minutes and we'll come back and answer that question at about 3:18. But let's take a 10-minute break now and give you guys a chance to decompress. Everybody, I think we've got most folks back up here again. Hopefully this class is making sense so far today. Reasonable, I hope. Does anybody have any questions about this Wronskian or this derivative operator L that we've been talking about? Does it seem okay so far? We've only done one example though, which was an easy one, which was, L was equal to what? D squared plus 1. And it was easy. We were able to just look at it and we figured out that sine of x and cosine of x were the solutions, and we were able to do the whole problem. But it's not always going to be quite that easy. So I would like to spend just a few more minutes here. We don't have too long to go on this for today. I just want to talk a little bit about how we could, in general, come up with the solution to one of these differential equations. Now, it turns out that this is the next section, by the way, that we're going to be looking at nth order linear homogeneous differential equations again. But in order to get any further progress, we actually have to add yet another word in here, which is constant coefficient. Okay, so let me just recall for you what this is looking like. What we have is, a naught d to the n plus a1 d to the n minus 1 and plus dot 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 plus an of y equals 0. Right, that's the setup of this. Keep in mind the word homogeneous here, right? That's referring to the fact that we have a 0 on the right-hand side. And then nth order is referring to the highest power of n that we see in the differential equation. Okay, so it's nth order, it's homogeneous, it's linear because of the nature of this form. And the constant coefficients is referring to A0, A1, A2, and so on. You might remember at the start of class today, I wrote it out as if those could in general be functions of x. They don't have to be constants. They could actually vary with x. But for this section, all of these a's are going to be constant coefficients. As long as I make all of these assumptions, I'll be able to solve the differential equation. We are going to learn, okay, there's going to be plenty of differential equations that by the end of the semester, we're still not going to know how to solve, but I promise you, it will not be these. These differential equations, we are going to learn how to solve fully in every situation, as long as it's nth order, linear, constant coefficient, and homogeneous. We're going to learn how to solve them. And it's interesting that the method for solving this. Okay, this is going to be a real letdown. I have a feeling it certainly was a letdown for me. This is why I ended up liking linear algebra the most. I still like differential equations, but I like linear algebra just a little bit more. And the reason is that the method for solving this differential equation, okay, try not to get too disappointed. We're going to guess the answer. Oh, I'm sure glad I got my PhD so I could do that. Right? As essentially, it sounds like a really crazy idea. We're going to guess the answer. No, actually, what really happened was somebody way smarter than me and way before I ever came along figured out a really good way to come up with a guess for this type of differential equation. And it turns out that the guess that we're going to use is y of x equals, so I'm just going to come out and spill the beans here, just tell you immediately what it is. We are going to guess e to the rx, okay? So we're going to guess this exponential function where r is some number, right? It's a number and it is to be determined. It is to be determined. So this is what we're going to hope that by just plugging it in, it's maybe going to work. There's a name for this kind of function. It's often in the book, you'll see the word trial solution or the phrase trial solution. So when I talk about a trial solution to a differential equation, I just mean that it is something that we're going to guess as a solution, okay? Now, when I say that we're going to guess this solution, what I need to do is try to plug it into the differential equation and see if there's any way that we could make it work, right? So I'm going to actually plug that in. So I'm going to plug in to the differential equation. Okay, so that just means I'm going to take a naught d to the n plus a1 times d to the n minus 1 plus dot 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 plus an times e to the rx, or I shouldn't say times, I should say applied to e to the rx, and I'm just going to set that equal to 0. And I'm going to see whether or not I can solve for r. Okay, so let's just try to work with this for a minute. Starting from left to right, I have a naught here, and then what do I have? I have n derivatives of e to the rx. Can you do that in your head for me? If I was to take n derivatives of, e to a constant times x, e to the rx, what would it give me? Can you think that through? Just how derivatives work with the exponential function? Like if I start with e to the 5x, and I take the derivative, what is it? 5e to the 5x, right? What if I take another derivative of it? 25e to the 5x. What if I take another derivative of it? 125e to the 5x, right? The 5 keeps pulling out in front, right? Every single time. In fact, it's going to pull out in front n times. So this is actually going to be r to the n e to the rx on that first term, right? So the r just keeps pulling down in front every time you take a derivative. Okay, then let's go to the next term. We have a1. This time I'm only going to do n minus 1 derivatives of e to the rx. So I'll be pulling down n minus 1 powers of r times e to the rx. And we're going to go dot, 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 and just keep doing this for all of the terms that we have. And then the last term is an e to the rx. Just as is, and we're setting that still equal to 0. Okay, does anybody see any algebra that we could do with that? Angela? Exactly, there's e to the rx in every single term there. Let's pull it out. So we would have a naught r to the n plus a1 r to the n minus 1 and plus dot 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 plus an. And then that's times e to the rx, and this is still equal to 0. Okay, looking pretty good. That's looking pretty good. Now, I have two things multiplied together equaling to 0, right? Well, we all know that if the product of two things is 0, then one of them is 0, right? Is e to the rx ever equal to 0 though? It sure isn't. There's no way to plug a number in for x and make that come out to 0. This part is not 0. The e to the rx piece is not 0. You can essentially get rid of it. It's not really, we're not really canceling it. I'm just saying that that part is not 0. And so the conclusion is that a naught r to the n plus a1 r to the n minus 1 and plus dot 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 plus an, that does have to equal 0. Because the other factor is not 0, but the whole product has to ultimately be 0. So the part on the left that's in those parentheses has to be 0. There is a name for this. I'm going to put this in a box. This is called the auxiliary equation. The auxiliary equation for the DE that we're looking at. That is the auxiliary equation. And one thing that is incredibly beautiful here, guys, is that the auxiliary equation is actually already staring at you way back from the very beginning. If we go way back to the very original differential equation that we have, and we want to know what's the auxiliary equation, my friends, it's simply a matter of turning all of the D's into R's. That's literally all you're doing. And this is why section 8.2, most people find it to be pretty chill. We can do this section in about 20 minutes of homework, you're going to be good to go. Essentially, the idea is they give you this, you change all the D's to R's. Now, your goal is to solve for R, right? R is to be determined here, right? So I'm looking for values of R right now. And here's the auxiliary equation. How many solutions for R will I get if I wanted to solve this auxiliary equation for R? Including repeats and including complex numbers, if I had anything like that, if I added all of those up, what would be the total number of values of R that you would have, including those repeats and complex roots? Chris?
N.
It would just be n, wouldn't it? Right? A quadratic equation always has 2 roots. A cubic equation always has 3 roots. A quartic equation always has 4 roots, right? The number of roots is always just simply equal to the degree of the polynomial, right? So this has n solutions for R. But I just want to be really clear about that because my class this morning kind of got a little tripped up by this. This is n solutions for R, including repeats. You might have the same root multiple times, and complex numbers. Okay, so if we include repeats and if we include complex numbers, then yeah, we'll get n values of R. And for each of those values of R, guys, we can make a solution to our differential equation that looks like this, e to the rx. Okay, remember, this is an nth order differential equation, which means that my solution set forms a vector space of dimension n, right? Which means I need n basis vectors. If it's dimension n, I need n basis vectors. And I think I'm getting a pretty good idea how I'm going to get them. Because anything of this form will serve as a solution for each of those values of R, and I've got n of those, right? This is exactly how we play the game. So let's just do a quick example here. And then I think you're going to really appreciate the idea here. Let's suppose I want to find the general solution to, let's take the differential equation y triple prime minus y double prime minus 30 times y prime equals 0. Let's say I wanted to solve that differential equation. So we're coming a long way today, right? We're making a lot of progress compared to when we woke up today. We would have had no idea how to solve this. Now, all of a sudden, this is gonna be easy breezy, okay? The first thing I would probably do on this kind of problem, and you'll want to do this on your homework as well, is to write down the D notation equivalent of this. So remember, if I give it to you with the primes, right, we need to be able to go kind of back and forth with the D notation. So in D notation, this is gonna look like the following, 3 derivatives of y, that's d cubed, right? And then minus 2 derivatives of y, which would be d squared, and then minus 30d, okay, so this is the D notation of y equals 0. So we still have that same expression. So far, I haven't solved anything. I'm just rewriting into the D notation if we wanted to use the D's, okay? But the reason that I like to put it in the D notation is that now I know that this auxiliary equation, right, this auxiliary equation, which we're going to need, is basically obtained by changing all the D's just directly to R's. We don't have to do this whole derivation again, guys. You don't have to do all this anymore. We just did it once to kind of show how it works, but at the end of the day, all I have to do now is go straight to the auxiliary equation. And so I'm going to put that here. Pretty much a piece of cake. It's just going to be r cubed minus r squared minus 30r equals to 0. Yeah, that's the auxiliary equation. And my goal is to come up with the values of r. It says here this has n solutions for r. On this problem, by the way, what is n here? In this example? It's 3, right? N is 3. So add that to the summary here. So n is 3. So I'm expecting 3 values of r. How would you propose that I go about finding them? Emptina?
You factor out the R.
Okay, yeah, we can do some factoring here. Maybe I'll pull this over here. R gets factored out and I'm left with r squared minus r minus 30 equals to 0. And from there, over here for a second. Thank you. Well, now I just have a quadratic. And maybe you see how to factor it easily, maybe you don't. Even if you don't see how to factor it, you can always use the quadratic formula. But in this case, it actually does factor quite nicely. R minus 6 times R plus 5, right? And so we get this factorization like so. And so as promised, we get 3 values of R, 0 and 6 and -5, right? And based on that, I can make 3 of these solutions now. I can write them down. Let's just do that. The first solution, I'll call it y1 of x. That would be e to the 0x. Of course, e to the 0 is just 1. Okay. And then we would have y2 of x, which would just be e to the 6x. And y3 of x would be e to the -5 of x. Okay, so we just make a solution of this form, right? E to the Rx for each of those. Okay, so that's it. That's it. These are going to be your basis. Okay, now I should point out that technically we need to hold our horses a little bit here. Okay, are we sure these are Li? Right, as always the question, because if they're going to be a basis, they have to be Li. And since there's 3 of them here, I can't just say that they're not scalar multiples of each other. I used that reasoning earlier with sine and cosine because it was just 2 functions. And with 2 functions, you can kind of get away cheap on that. But here we have 3 functions. So you can't just say, oh, they're not scalar multiples of each other. So what would you do instead? It's the big word that starts with a W. Hold your horses. Somebody I haven't heard from today? Remember what it was? Yes, Maxwell.
Wronskian.
Thank you for bailing me out. Yes, it is the Wronskian. The Wronskian is our go-to test for linear independence, right? So I would just make a little note here that we could use the Wronskian. Use the Wronskian to test for Li. It turns out, though, we're not really going to need to do that. I know you might be feeling right now like, oh, every single problem we're going to have to do a Wronskian, right? What if Dr. Annan gives us a 7th order differential equation and there's 7 values of R? Are we going to do a 7x7 matrix with a Wronskian? I don't think so, right? It's going to be a little bit too much to do that by hand. But it turns out that when the roots of your auxiliary equation are distinct numbers, if we don't have any repeats, then it will always be the case that when you build these functions, they will be Li. I'm going to have us prove that in some group work. Not today, but in the next couple classes, we'll do some group work to prove that, at least for the case of 3 roots. Okay, so these are always going to be Li by using that Wronskian test, but we're not going to do it every time. Am I making sense? We're going to kind of like generally understand that this is going to work in a general scenario and then just apply it in this kind of a situation. So these are Li. Yeah,
You
Marcus.
said if the solutions are not scalar multiples of each other?
I'm sorry?
You said if the solutions are not scalar multiples of each other?
No, I said if these roots are all distinct, if there's no repeats, then when you build these solutions, they will definitely be Li. The scalar multiples thing only works for 2 functions, right? Yeah, Audrey?
So we don't have to show any work for,
So you're not gonna have to show the work for the Wronskians here. Yeah, that's gonna be the point. It's kind of just bypass that, right? So I'll just say omit. Okay, we'll just omit that piece. But if these are Li, and if my solutions form a 3-dimensional vector space, then guess what, guys? This is your basis. This is your basis, and your general solution, we can go ahead and write it down now. Your general solution becomes, this is the answer that we're looking for, y of x equals, okay, so here it comes, C1 times 1 plus C2 times e to the 6x plus C3 times e to the negative 5x. That would be the final answer. That would be totally the final answer there. Okay? Does this seem pretty easy? You just write down the D notation, immediately convert the D's to R's. It gives you an auxiliary equation. Then you find the roots there. Now, it is pretty easy. It's not quite as easy as I'm trying to get away with here. I mean, after all, a few minutes ago, we did this one. And that's also nth order linear constant coefficient homogeneous, but we did not ever use e to the rx here. And in fact, the solutions turned out to be sine of x and cosine of x. Where does that come from? I don't see that in my guess of my answer at all right now. So there's something a little funky going on with that. Why is this sines and cosines? I can give you the short answer today and I'll explain it in more detail next time. If you write down the auxiliary equation here, it would just turn the D's into R's like so. And the roots here, oh, here we go. They are complex numbers, okay? So we don't see any complex numbers on this example, which is why everything turns out so nice with these exponential functions. But I don't think your boss, if you're out and working for an engineering firm, and if you tell them, oh yeah, the solution to the problem is e to the 3 plus 5i times x, that they're going to be too happy with you. So if your R value has imaginary numbers in it, then this is the way you would write it based on the box over there, e to the Rx. But if I look at this, if you hand this to your boss, you could end up without a job by the end of the day. It's like, I can't even try to plug a number for X into your calculator. It's not going to give you an answer. And try to draw a graph of that. I have no idea how to even draw a picture of this thing. It's not a meaningful solution. It's not a real world solution that an engineer would be looking for. So somehow this is not going to be an acceptable answer, but the hint that we have right now is that somehow we can bail ourselves out using sines and cosines. So I'm going to show you that on Thursday. I'm going to make you come back 48 hours and we'll talk about that next time. And when we have complex numbers showing up, we have to deal with rewriting things with sines and cosines. It turns out it's very easy. It's not going to be a hard thing, but we just have to understand that there's something there. So I'll come back to that next time. Are there any questions on this example though so far? As long as the roots are real numbers, these e to the r x's are great. They work brilliant. That's probably it for new material for today then. I'd like to just spend whatever time I have left looking at these problems from chapter 7. So maybe we could open up the homework for a minute. We don't have a huge amount of time, but I think we have enough time to look at a little bit of this. So does that sound good then? No questions so far? All right, great. So on 7.1, number 20, I'm going to go quick so that I can talk as much as possible about these. This one was up on the board over here on the sideboard. We have the following matrix. So we're changing gears, guys, for the last 10 minutes today, just to talk this through. 10, -12, and 8 on the first row. The second row is going to be 0, 2, and 0. And the third row is -8, 12, and -6. And they just want you to find the eigenvalues and eigenvectors. So that's a standard question here. The first thing we would need to do on something like this is work out the characteristic equation, right? So we would take the determinant of the matrix we get when we subtract lambda off of the main diagonal. So I'll just very quickly show you that piece of it. So subtract lambda off of the main diagonal of the matrix that they gave us. So that's the matrix. And does anybody have any suggestions for me about doing this determinant? Audrey? Yeah, the second row has a lot of zeros on it. So if I do cofactor expansion on that second row, I'll have this 2 minus lambda term right here. I'll cross off this row and column. And that gets multiplied by what? The determinant of the 4 numbers on the outside, or the 4 expressions on the outside. I'm just going to write it out in big brackets here. We would have 10 minus lambda times -6 minus lambda, and then it would be plus 64. Okay, we get plus 64 on that. Remember from last week that my advice is don't multiply this all the way out, because the goal is actually the opposite of that, which is we want to get it factored. So I would just leave this 2 minus lambda in front, as is. The part in brackets will only be a quadratic equation, so I'm kind of sounding like a broken record because we did this exact thing last week. But if you worked out this quadratic, you would have, lambda squared, and then minus 10 lambda plus 6 lambda, which is actually minus 4 lambda. And then you have -60 plus 64. That's a net total of plus 4. So that becomes the equation. And now this part in brackets is just a quadratic, which actually factors nicely. It just factors as lambda minus 2 quantity squared, like so. And what are my roots going to be then, guys? 2, 2, and 2, right? If I set this equal to 0 now, which is the way we usually handle these eigenvalue calculations, we just set that one equal to 0. Then I get my lambda values of 2, 2, and 2. Okay. It's definitely a good idea to get in the habit of checking those. check this against the trace of the matrix. If you add up the main diagonal, it should add up to 2 plus 2 plus 2. Right? So the diagonal has to add up, and then the product of these numbers is 8. So if you were to take the determinant of this matrix, you should get 8. That's the other fun fact about the eigenvalues. But guys, the nice thing here is we only have one eigenspace. We only have to do one null space calculation, which is subtracting 2 off of the main diagonal here. So if I do that, if I subtract 2 off of the main diagonal, okay, so I'll get 8, negative 12, and 8, and then I'll get negative 8, 12, and negative 8. And remember that you always have to be able to cross off a row because this matrix can never be invertible. And in this case, though, unfortunately, the row that we get to cross off for free is the row of all zeros. That's the only thing we can say for sure. However, you probably notice that the first row and third row, they are also multiples of each other. So you can cross off, in this case, not every case, but in this case, we can actually cross off 2 rows. Cross off 2 rows, we get one pivot right here. And this means if I look at my variables,